Thank you. Hello. As mentioned, I'm Nick Heersema, and today I'll be discussing heat flux requirements for electrified aircraft wing anti-ice systems. As the push for increased efficiency and decreased emissions drives the aviation world towards more electrified aircraft, the availability of excess power or engine bleed air for icing protection of wing leading edges diminishes. The requirements for such a system need to be considered early in the design process. The work I'm going to present today was funded under the Convergent Aeronautics Solutions CAS HEATHER project. HEATHER, or the High Efficiency Electrified Aircraft Thermal Research, has two primary goals. We want to increase the efficiencies of electric components to reduce the waste heat generated, and then manage that waste heat using passive thermal management systems. 3 different concept aircraft that cover different types of electric aircraft are analyzed. Stark-Able is the single-aisle turboelectric that has 2 underwing turbofans that drive an aft electric boundary layer ingestion, or BLI, motor. Pegasus has 2 turboprop engines with parallel electric boost on the outboard locations and 2 all-electric inboard engines for takeoff assist, as well as an aft all-electric BLI motor. Our VLT tilt wing has 1 centrally located turboshaft engine with 4 electric wing motors. A common thread across all these aircraft is that the conventional engines are smaller and supplemented by electric engines, so there is a concern that they won't be able to support conventional ice protection systems unless the requirements for that system are included early in the design process, which is what we're doing here. The conditions that we want to analyze for icing are determined by the expected flight profiles. Stark-Able is a single-aisle narrow body, similar to a 737 or an A320, so it has a similar flight profile. The cruise altitude is above normal icing conditions, so an analysis would be focused on takeoff, climb, descent, and holding. This particular analysis, we focused on takeoff and climb when the least amount of bleed air or excess power is available. Pegasus has a flight profile similar to a regional jet that is shorter and lower in altitude than Stark-Able. That lower altitude places the cruising altitude within typical icing conditions, so all phases of flight must be considered. But again, for this analysis, the focus is on takeoff and climb for the same reasons. Our VLT is a little different. Its flight profile is designed for urban air mobility. You have several short hops at low altitude. Given that low altitude, you could encounter icing conditions during all phases of flight. The analysis for this one is a bit more challenging since both forward flight and hover mode must be considered. And on each of these slides, the icing conditions that we analyzed were listed. So for those of you who aren't overly familiar with ice protection systems, there's 2 primary types currently in use on most commercial aircraft: thermopneumatic and electrothermal. Thermopneumatic uses bleed air extracted from the engine, fed through ducting, manifolds, valves, and pipes to get to the leading edge. Because of all of that, it has higher weight requirements than, say, an electrothermal system. It also has a performance penalty while the system is active due to the bleed air that's being extracted. And it's capable of transferring approximately a few kilowatts per meter span based on the information available in the literature. The other type of system is the electrothermal system. It's used primarily for propeller blades and windshields. It's also used as a wing anti-ice or de-ice system on smaller planes, and most recently it's in use on the 787 Dreamliner as the wing de-ice system. It has reduced energy requirements, drag, and noise compared to a thermopneumatic system. Unfortunately, the heat transfer capabilities were not available in the literature, so I wasn't able to compare the heat transfer requirements to an electrothermal system for this analysis. Additionally, types of ice protection systems can be delineated as running wet or fully evaporative, and they're pretty much what they sound like. A running wet system heats the incoming water to maintain the temperature above freezing so you get liquid, over the heated section of the wing chord. The downside is that liquid water can then refreeze on the wing after the heated section, which is called runback ice. In many cases, a de-icer is required to handle the runback ice. It does have lower heat transfer and power requirements than a fully evaporative system, and it's commonly employed as a parting strip on the leading edge of the wing to assist with de-icing. You can see in the picture that the heat flux requirements are lower than the fully evaporative system, but they're more spread out over the whole of the section that we want to keep heated and ice-free. A fully evaporative system, on the other hand, evaporates all incoming water on contact. There's no runback icing, so you don't need a de-icer. It is localized to a very small area around the leading edge of the wing, as you can see in the picture, but it does have significantly higher heat transfer and power requirements. And that's the kind of system used on the windshields or anywhere where runback icing is not permissible. I've also mentioned de-ice and anti-ice. An anti-ice system maintains the region ice-free. A de-icer, on the other hand, allows ice to build up to a certain level and then sheds it using different mechanics. And it's commonly set up to do so in a cyclical fashion to successive sections of the wing. And that reduces the total power or bleed air required. So for the analysis, heat flux requirements were calculated using LUICE, which is a software developed by the Glenn Research Center icing branch. For this initial analysis, as only the heat flux was of interest, a 1D steady state analysis was sufficient and a lot faster. A more refined 2D analysis is currently being performed by the icing branch using a software called ANSYS FENSAP ICE. The maximum heat flux that's been calculated with FENSAP so far is lower than the results from LUICE, so the LUICE results are considered more conservative, which is useful at this stage. Since aircraft tend to be moving more towards composites, given their strength to weight benefits, a typical aircraft carbon fiber reinforced polymer material was used for the skin in this analysis. A few scenarios were also analyzed using 6061 aluminum to understand the sensitivity to the skin material, and it was found that the heat flux requirements were approximately 3% lower, which was not considered significant at this stage of the analysis. The overall heat flow calculations assume that the entire wingspan is covered by the ice protection system. In reality, it is likely that some sections of the wing would be left unprotected due to the difficulties of integrating the system or analysis which determines that it's unnecessary to cover a specific section of the wingspan. Such an analysis is beyond the scope of this initial study, so for an initial estimate, we assumed that the whole span of the wing will require an ice protection system. The icing conditions that were selected are a mix from a NASA Common Research Model and platform-specific icing flight conditions. The last two scenarios for both Stark-Able and RVLT cover more severe intermittent icing conditions, which may not require the wing to be entirely free of ice for the short duration. It's important because they end up having a higher heat flux requirement, which I'll get to. A more refined analysis would be required to determine the impact to the handling characteristics and performance of the aircraft from ice buildup in different regions of the wing to determine if the ice that we build up would be acceptable. The heat flow rates necessary to maintain the front 10% of the chord across the whole wingspan ice-free were calculated and compared to the capabilities of a thermopneumatic system, since that's what we have information for. The color coding here is that red exceeds the capabilities of a thermopneumatic system, orange is on the upper end of the capabilities of a thermopneumatic system, and green is on the lower end. So green is good, orange is fine, red is a bit concerning. The conclusions here is that the running wet system is within the capabilities of a thermopneumatic system for all the scenarios analyzed. A fully evaporative system is within the capabilities for all except the two severe intermittent cases, so we'd have to do further analysis to determine if that's acceptable or not. The last column shows the maximum heat flux at the leading edge for a fully evaporative system, and it highlights one of the reasons why fully evaporative systems may not be suitable for this application, as the heat fluxes are very high and may exceed the abilities of the material and the selected anti-ice system. Pegasus has much higher heat flux requirements, which for the most part exceed the capabilities of a thermopneumatic system. Some options we could consider would be to use the thermopneumatic system as a de-icer instead, because that has overall lower requirements since only part of the wing is heated at a time. We could also consider reducing the area covered. Less of the span covered means lower heat requirements overall. Both options would require a more refined analysis to determine the effect of ice buildup on the aerodynamics, performance, and handling characteristics of the aircraft to determine what thickness of ice would be acceptable before it has to be shed. For RVLT, you'll notice that everything is red. All of the scenarios we analyzed exceeded the capabilities of a thermopneumatic system. A potential cause for this is that Loo ice is not really designed to handle the complicated flows immediately downstream of a rotor, so the validity of these results is in question. A more refined analysis is in works in FENSAP by the GRC icing branch, which would provide more realistic results. If, like with Pegasus, it still largely exceeds the capabilities of a thermopneumatic system, we have the same options to decrease the total heat flow rate. Thinking ahead to the future, some integration considerations. The heat flux at the leading edge required for a fully evaporative system might not be achievable given material and heat transfer constraints. So it would be more likely that we'd go with a running wet system. Running wet systems, for the most part, require a de-icer to handle run-back ice. However, we'd have to do more detailed analysis to determine the effect of the run-back ice on the handling characteristics and performance to determine if we need a de-icer or not. A de-icer does add weight and power requirements compared to a fully evaporative system. One fairly recently developed system is called EMEDS, or Electromechanical Expulsion De-icing System. It's in use on several aircraft, mostly general aviation aircraft and a couple of military aircraft, but it's a lightweight and fairly low power option. So for Stark ABL, for instance, it would take approximately a kilowatt of power and weigh 23 kilograms-ish, which is not bad compared to current thermopneumatic and electrothermal systems. And then the power requirement could potentially be reduced even further through the use of an anti-ice coating, which makes it easier to shed the ice. It doesn't prevent the ice from building up on its own. The conclusions: heat requirements were calculated for maintaining an ice-free leading edge for all three Heather variant aircraft. For the most part, the heat requirements were in excess of the capabilities of a typical thermopneumatic system. Further analysis would be required to determine the heat requirements for a cyclical de-ice mode for at least Pegasus and RVLT, and it would be a good idea to do it for Stark Able as well to potentially reduce the overall system requirements. A more refined analysis is required for RVLT, especially since Loo ice is not designed for the wing surfaces directly aft of the rotors, so those results may not be valid. And then additional analysis would be required for all three aircraft if we wanted to do a cyclical de-ice mode to determine the effect of ice accretion on the aerodynamics and handling characteristics. Such an analysis would also tell us if there's areas of the wing that we could leave uncovered without detriment. Additionally, it's desired to do some testing to validate the results because the takeoff angle of attack for Stark Able and Pegasus is above the range previously validated for Loo ice. Some acknowledgements. I'd like to thank Convergent Aeronautics Solutions for funding the project. NASA Glenn Research Center icing branch has been a big help. Eric Stewart helped determine the icing conditions to analyze and has been working with FENSAP to generate the results in that software. And Bill Wright was of help getting Loo ice up and running and helping determine what form of analysis would be most suitable. Additionally, NASA Ames Research Center provided CFD analysis in support of this project. My contact info is here. If you have any questions in the future, you're welcome to reach out, and I will take whatever questions we have time for now.